Welcome to the 10th presentation in the 4th webinar series presented by the International Adsorption Society. The IAS is an international organization dedicated to advancing adsorption as a solution to scientific, engineering, and human welfare challenges through the promotion of adsorption research and education. We thank everyone for attending the webinar today. The webinar series has been an immense success. The recordings of previous webinars continue to be viewed on YouTube and Bilibili. This is the 10th webinar of our 4th series, which we will continue to have monthly throughout the year. We intend to continue with a variety of different speakers from industry, academia, and other research institutes, as well as PhD students and early career researchers. Announcements regarding the 4th series will be distributed through the IAS mailing list and the IAS Twitter feed. Today's webinar will be given by Professor Andrea Laybourn at the University of Nottingham in the United Kingdom. I'm Nicholas Wilkins at Sponte Technologies Incorporated in Canada. Today's webinar will be moderated by Giuseppe Pizzella at the King Abdullah University of Science and Technology in Saudi Arabia. We are required to remind attendees and future viewers that the views expressed by the speaker, host, or other moderators are not necessarily those of the IAS or the institutions associated with those individuals. We ask that you consider joining the IAS as a regular member if you are not already. Our dues are minimal, only $20 US per year, but support the publication of our flagship journal, Adsorption, contribute to travel grants and workshop seed funding for IAS members and affiliated groups, as well as aid the organization of our triennial conference on the fundamentals of adsorption. Members also receive free access to IAS supported materials, including our journal, as well as the adsorption database published by Springer Materials. Anyone can follow the IAS on Twitter at @adsots for future updates regarding IAS events, webinars, and information about scientific meetings. Please help us expand our YouTube channel by liking this video and subscribing. I'll now hand it over to Giuseppe, who will moderate the YouTube Q&A.
Hi, it's my pleasure to welcome Professor Andrea Laybourn to today's webinar session. Dr. Andrea Laybourn received her Master of Chemistry and PhD from the University of Liverpool in 2008 and 2012, respectively. Her doctoral studies, under the guidance of Professors Andy Cooper, Dave Adams, and Jaroslav Kimiak, focused on the synthesis of porous amorphous networks and their molecular level characterization by solid-state nuclear magnetic resonance. Upon completion of her doctorate, she moved to the University of Nottingham as a postdoctoral research fellow, working across the School of Chemistry and Faculty of Engineering with Professor Martin Schroeder, Neil Champness, and Sam Kingman. She held a prestigious Nottingham Research Fellowship awarded by the University of Nottingham from 2016 to 2019. She is currently an assistant professor in the Advanced Material Research Group in the Faculty of Engineering at the University of Nottingham. She is also co-founder and secretary of the Royal Society of Chemistry, RSC, Porous Material Interest Group. She received the 2023 Barrier Award from the RSC for outstanding contribution towards developing the sustainable synthesis of porous materials, with a particular emphasis of microwave and continuous flow synthesis. During the webinar, questions can be submitted to the speaker as comments on the YouTube live stream. Questions will be answered at the end of the presentation. With that, I will welcome Professor Andrea Laybourn again and pass over the presentation to them.
Okay. Sorry about this, folks. Just trying to figure out which screen to share. This one. Okay. Can you just confirm that everything's on the screen and that you can hear me correctly?
Exactly. We can see your screen and the laser pointer as well.
Thank you very much. So thank you very much for the kind invitation, and thank you to the International Adsorption Society for hosting me to talk to you today about some of the work that we've been doing in the synthesis of metal organic frameworks. And I'm going to be focusing today on the synthesis using microwave and flow technologies. So I'm going to talk to you, or splitting my talk up into three particular areas. So first of all, I'm going to talk to you about metal organic frameworks and particular interests that we have within the group in synthesizing these materials and their applications that we have interest in, and why we are interested in using microwave heating. So I'm going to give some examples both from our group and from the literature in this area. And then the next section of my talk is going to be digging deeper into the mechanism of microwave heating in MOFs and having a look at the impact that microwaves can have on the synthetic outcome of MOFs, particularly focusing on the microwave parameters for this. And then towards the final section of my talk, I'm going to move on to talk about combining continuous flow and microwave heating technologies and some of the results that we've gotten in this area. So first of all, I'm going to talk to you about MOFs and talk to you about microwave heating examples from the literature. So hopefully most of you will be familiar with metal organic frameworks. So from our perspective, metal organic frameworks are particularly interesting because they have very tailorable structures. You can synthesize these from a metal node and an organic linker. They form extended frameworks, typically with porous voids within them. And by having a look at different combinations of metal nodes and different combinations of organic linkers, you can get a wide variety of different structures, functionalities, and therefore properties from this class of material. So these are examples that I've pulled from the literature, which show some of the different structures, and depending on the chemical functionalities as well, they are interesting for different types of applications and can be tailored towards those. So within the group at Nottingham, we are particularly interested in the applications on this slide. So this is a range of applications that we study in collaboration with people in the Advanced Materials Research Group at Nottingham. So we're interested in the gas storage and separation and purification across a wide variety of different gases from CO2, hydrogen, methane, and so on. We're also working towards developing metal organic frameworks for sensing devices, particularly in the healthcare sector. We are also working towards looking at being able to capture guests within the metal organic frameworks and use the properties of the frameworks to be able to catalyze reactions of those guests into useful products. We're also interested in energy applications. So we've got MOFs that we're interested in looking at for fuel cells and for battery applications. One of the PhD in the students in the group has been pioneering porous magnetic materials, where he has been making scaffold structures and then attaching metal organic frameworks to those, which imparts hierarchical porosity properties, but also has the added benefit of being magnetic at room temperature, meaning that you can use a magnetic field to be able to fluidize these materials for separations, or be able to use an induction heating setup to be able to heat these materials and improve their heat transfer, something which was coined by Matthew Hill's group based in Australia. We are also interested in looking at wastewater treatment, toxic gas capture, and all these properties and applications and areas of interest. We are interested in trying to develop materials which have a positive social and economic impact. So that is setting the precedent for these particular applications and why we're interested. Now, central to these applications and areas of interest to us is the synthesis of metal organic frameworks. But as we know, there are a range of challenges that are present in MOF production, and these are present even at laboratory scale, right the way up to industrial scale manufacturing. And these are that the metal organic frameworks can typically be expensive, particularly if you've got an intricate linker or a rare earth metal, for example. When synthesizing these materials and then activating them, sometimes if the materials are particularly delicate, they can suffer from loss of porosity, which is a disadvantage, especially if you're interested in the adsorption properties or the host-guest properties. There has been a lot of work going on, particularly by many groups across the world in developing an understanding of MOF crystallization. And Hamish Young has been one of the people who's been making good headway in this area. By having a limited understanding of MOF crystallization, that can hinder us being able to synthesize these materials in a controllable manner and trying to understand where this loss of porosity and issues with reproducibility come from. So a lot of people are working in this area and making excellent progress here. As I mentioned, the reproducibility of the materials can be quite a challenge, and Hannah Borstrom and Bettina Loch and co. have published a paper recently where a metal organic framework, a zirconium metal organic framework, was synthesized in a range of different laboratories across the world, and having a look at the reproducibility and where this reproducibility issue came from. So there's some exciting work trying to unravel what's going on there. Other challenges in the synthesis of MOF production is that typically you can use organic solvents, so dimethyl formamide, to produce these materials, and the reactants can be corrosive. And so there's been excellent progress in trying to overcome these issues by looking at more sustainable synthesis. So why are we particularly interested in looking at microwaves? So I've put a range of benefits up on this slide. And as you can see from these benefits, microwaves do lend themselves towards improving the sustainability of the synthesis of metal organic frameworks. So microwave systems can be started up and shut down very, very quickly, which means their reactions can also be very quick as well. So typically conventional heating reactions take hours, sometimes days, whereas microwave synthesis can be on the minutes to seconds timescale. And I'll go on to talk about some examples from our group where we've really gone down to very, very fast reactions with the technologies we've developed. There is energy efficiency to be gained from using microwaves if you are able to deliver the microwave energy to the reaction mixture and do that in a controllable way. There are a plethora of examples where microwaves have been used to improve the properties of metal organic frameworks. So there's been a lot of work looking at the phase purity, the control over the morphology and particle size. And microwave heating has also been shown to improve the porosity of some materials. The reactions are able to produce less waste, so you can reduce the amount of solvent when you're using microwave synthesis. And you can also, if you are synthesizing the material, the desired material, you can produce less waste, such as side products, and I'll come on to some examples of that as well. And importantly, microwave technology also has an increased capacity for the same plant footprint. So by that, what I mean is microwave heating is a process intensification method, and you can really get intensified small reactors which operate in a continuous flow manner, and being able to produce a lot of material in these short times in a short footprint for the reactor. Recently, I had the pleasure of working with Ahmad Desai and Romy Ettingler in Russell Morris and Rob Armstrong's group to have a look at writing a review paper on the microwave heating of sustainable MOF synthesis in combination with some of the excellent work that's been taking place in, say, room temperature synthesis and mechanochemical synthesis as well. So I wanted to highlight the advantages of microwave heating, which we've reported in that paper. So we've got a range of different areas where microwave heating has been used. So at the laboratory scale, we've got synthesis of metal organic frameworks and other reticular frameworks indeed, which are covered in that report. Microwave heating has also been used to look at the workup and activation stages of metal organic frameworks and other reticular materials. And also there's a couple of examples that I want to touch on where the area is starting to move towards continuous flow and high throughput production of materials. So to go a little tiny bit deeper into the laboratory scale syntheses, there's two examples. There are a lot more in the review paper, so I do encourage you to have a look at that. The two that I wanted to focus on today were the dry gel conversion, which was developed by Tanner et al. And this is using a reactor where you have a solvent at the bottom and then you have a shelf essentially with solid reagents which have been finely ground together, and you're using microwave heating to evaporate the solvent into the layer above where the solid reactants are, and then the reaction takes place in the vapor phase. This is a relatively fast process, under 3 hours compared to the conventional heating processes. And you can use solvents of less than 10 milliliters. So this is reducing the impact of the solvent there. And then Lanchas has gone further and has also reported some solvent-free preparations of a couple of MOFs. I've listed two there. There are others where the solid reagents have been mixed together, and then microwaves have been used to heat these materials. And so this is producing MOFs in solvent-free conditions. But a slight disadvantage of these approaches is that the materials produced can suffer from a loss of crystallinity, and also the surface areas tend to be roughly half to what you would expect for the materials and what's possible via other methods. And I also wanted to highlight a synthetic procedure that one of the PhD students in the group had developed. So this is the synthesis of NOT 300 or MFM 300, which is made by reacting the biphenyl tetracarboxylic acid. We're using aluminium trichloride hexahydrate in this case. We're performing the synthesis in water in 10 minutes using a microwave reactor and off-the-shelf system. This produces the MFM 300 aluminium framework. This framework has a aluminium oxygen secondary building unit. It's a channel pore material, and the linker bridges between these secondary building units. Now, the reason why I wanted to highlight this synthesis is because we saw some interesting effects when we were preparing this on the porosity of the materials. And what we found when we measured the carbon dioxide uptake was that at roughly around at around 273 Kelvin and 1 bar, we were able to produce a material which had an uptake of carbon dioxide of 8.8 millimoles per gram. So this was 26% higher than the conventionally prepared MFM 300 material, which is 3 days solver thermally and uses a piperazine modulator in there. We don't use the piperazine modulator to produce this material. We do get the pore widths that we would expect and that you get with the conventionally prepared material, so roughly around 0.5 nanometers for the pore widths. But this material is also very well studied for sulfur dioxide and nitrogen dioxide uptake as well. So we investigated the uptake of this with our collaborators based over in Leipzig, and we found that the sulfur dioxide uptake, which is 8.5 millimoles per gram at 298 Kelvin and roughly around 0.2 bar, and the nitrogen dioxide uptake is 1.9 millimoles per gram at the same temperature and at 0.01 bar. And these results were quite astonishing to us because they are for the sulfur dioxide, it's 70% greater uptake in the capacity for the microwave synthesized material. And for nitrogen dioxide, it's 90% greater uptake for this material. To add to our interest as well, the conventionally prepared material is not porous to nitrogen. However, we had a look at the nitrogen uptake to see if we saw any differences, and we did find that we got some nitrogen uptake for this material. Now, in order to rationalize this, this uptake with the dioxides, we know that from studies done in the Schroeder and Yang groups in Manchester and in Illich Ibarra's team based over in Mexico, that the MOF, the interaction between the MOF and the dioxide pollutants are typically across this secondary building unit backbone via an aluminium hydroxyl interaction. Because this material has not been prepared porous to nitrogen other than by our hands, we do not yet have a reason why, or a proven reason why, this material uptakes nitrogen. What we think might be happening, and our current working hypothesis is that we are producing an MFM 300 framework that is defective, and so this is allowing the nitrogen to penetrate into the structure, which you don't see with the conventionally heated material. But we do have this currently ongoing investigations in the group to further uncover information about this. So I want to now touch on a couple of examples in the literature where microwaves have shown excellent promise for the workup and the activation of metal organic frameworks. So I've got an example where a team has looked at zirconium MOFs, where the acetic acid modulator coordinates into the MOF structure, and this could be removed by essentially heating up the materials in water, and the acetic acid then dissolves in the water, removing that coordination with the zirconium MOFs. And there's another report as well which has looked at the removal of solvent from HCO1. Now in this case, what the team had a look at was preparing HCO1, which you get a solvated structure, then saying, can we use microwaves to heat this structure and then evaporate out the solvent that is contained within that structure? And that's what they were able to demonstrate. So they could do this on the minutes timescale, between a few minutes up to 35 minutes, and for a range of different solvents, including methanol, ethanol, acetonitrile, and DMF. So essentially, they were able to heat the solvent contained within the pores and evaporate that out to give you a completely desolvated material, which you can then look at host-guest interactions and absorption from this. A review that we've written with one of the PhD students in our group, Luke Woodliff, has also had a look at reviewing the workup and the activation and focusing this in terms of the sustainability drivers for this and next steps. So if you're interested more in having a look at this, I'd recommend that you have a look at that review paper. We do also look at other methods of workup and activation where microwaves is considered along these other technologies. And then finally, for the literature precedent, I wanted to talk about some high throughput examples where some excellent progress has also been made in this area. So there are two examples I want to highlight, both from Berenschmidt's group where the first example is the synthesis of an aluminium porphyrin containing MOF, the structure of which is shown here. And what the group did is they used a high throughput batch microwave reactor combined with machine learning and optimized the synthesis via a couple of generations to be able to produce a highly porous and crystalline material of this aluminium PMOF. So this is an excellent example of being able to use machine learning in combination with the rapidity that you get with microwave heating. And then the Schmidt group have also reported the synthesis of HCO1. And in this particular case, what they did was they were looking at extracting the chemical intuition out of the syntheses from both the successful and the unsuccessful reactions in the synthesis of HCO1, and then applying that knowledge within the machine learning programs that they developed to look at trying to synthesize the zinc analog of HCO, which requires very different reaction conditions than the copper analog. And what they were able to do was to have an excellent starting point from all the knowledge that had been gained from the synthesis of the copper analog and apply that to the zinc analog without having to go back to starting from scratch with this. So these two examples really show the rapidity in which we can have a look at optimizing the porous materials using the combination of machine learning and microwave synthesis. I have also mentioned here some continuous production, and I'll talk about that towards the end of the talk as an example from our group at Nottingham. So now I've talked to you about some of the examples in the literature, why we're interested in MOFs and why we're interested in using microwave heating. But I want to use the next part of the talk to go into the mechanism of which microwaves are heating the MOF reagents, and then look at the impact of that on the synthetic outcome, and taking that as a view towards when we are moving from the laboratory towards industrial scale processes or continuous processes, what are the important things that we need to consider? So really digging in deep there as to what's going on with our microwave reactors. So hopefully you will all be familiar with a kitchen microwave oven, which I've shown here. We have a section where you would put the material that you want to heat, and we call this the cavity. You also have the power setting as well, and the timer, and then the energy is delivered by the magnetron. What you might be less familiar with is how the microwave field propagates within that cavity. And that's what's shown on the graph here. So you can see that we've got areas of high microwave field intensity, which is shown in the red on this graph. And then we've also got areas of low microwave field intensity shown in blue. And that is particularly important because you want to be able to design your cavities to have the maximum microwave field intensity exactly where you want to deliver it into your MOF reagent mixture to be able to efficiently synthesize these materials without wasting any energy. Importantly, when you put the reagents into the microwave cavity, you do get some attenuation of the microwave field because the reagents that you've put in or your reaction mixture can absorb, you can get things that reflect, and you can get things that attenuate that microwave field. Now, I've mentioned and touched on a few times the energy efficiency, where microwaves have been shown to have a positive influence here because of the shorter reaction times. But I wanted to really emphasize this with a video. So what I'm going to show you here is a video where I've placed some bulbs inside a microwave reactor. For a disclaimer purpose, I do not recommend that you do this. This is a risk that I've undertaken within the group. And so what we're showing here is how the energy efficiency is important through this demonstration. So what you can see is that as the bulbs go through an area of high microwave field intensity, they are illuminated. When they are going through an area of low microwave field intensity, they are not illuminated. Now, the key take-home message from this is that the magnetron is on the whole time that these bulbs are going around on the turntable inside this cavity. So the bulb at the front is in a high area of microwave field intensity, where the bulbs at the back are in a low area. The magnetron, however, is on the whole time, and so it is delivering energy into this cavity. At laboratory scale, the efficiency of the energy might be relatively low in this case, but when you look to developing continuous systems or industrial scale systems, it is really important to be able to deliver that energy exactly to where you want it to go, so that you can make these materials in an efficient way. So how do we know what is happening in the reaction mixture, and how does that affect what we're interested in treating? So typically, laboratory-based microwave systems and conventional kitchen microwave systems operate at 2.45 gigahertz. And what this means is you have a microwave field which is oscillating. It's going from a high to a low electric field potential. You have, on the case of the left-hand side, I've got some water molecules, which at the start, when I pressed on this slide, we're wiggling backwards and forwards, trying to keep up with the oscillation between high and a low microwave field intensity or electromagnetic propagation. On the right-hand side, we've got ionic conduction, which is if you have ions present within your reaction mixture or within the material that you're treating, then what these do is the ions also move relative to the high and low electric field potential. In both cases, because you've got the dipolar rotation or you've got the movement from the ionic conduction mechanism, these molecules are vibrating against each other and rubbing against each other and creating friction, which leads to the heating. And so these are the underlying mechanisms that would happen at this particular frequency of the electromagnetic spectrum. Now, in order to understand beyond the mechanisms of synthesis, of microwave absorption, we also want to know whether we've got any differences or how the heating will happen within these reaction mixtures. And this is governed by the dielectric properties. So what we've got here is the dielectric permittivity, or the dielectric constant, plotted on the y-axis, and on the x-axis, we've got the loss constant, or the dielectric loss. So what we did was we measured a range of metal salts and a range of MOFs and linkers, and had a look at how they would looked at their dielectric properties, and we're then looking to see how they would interact with a microwave field during the synthesis. We also benchmarked this against a range of materials that you would typically get, which are not very microwave absorbing and stay cold if you put them into a microwave reactor. And these are typically used to make the microwave reactors themselves. So we can see that if you have a low dielectric constant and a low dielectric loss, then you're going to be in a situation where you would expect your reagents to be cold. Whereas if you have a high dielectric constant and a high dielectric loss, then you would expect your materials to heat very rapidly within the microwave field. And we can see that for the example of the MOF reagents, we've got the metal salts, and these are up with salty water and water itself up in this region. So these will get very, very hot. Ethanol will also heat very well in a microwave field. Now, the MOFs themselves and the linker here, I've shown terephthalic acid as the linker. The same is true for the trimesic acid linker. These have medium dielectric permittivities and quite low dielectric losses. And so these will stay relatively cool. And so it's the solvent and the solvated metal ions that will be heating from these dielectric properties measurements. That would be our hypothesis. So anybody who knows me well knows I love a good analogy. So on this particular example, I wanted to use the analogy of placing a food item, in this case, a meat pie, into a microwave oven, and use that to explain the analogy that we have with metal organic frameworks. So if you've ever placed a pie in a microwave oven, you may notice that that the pastry stays relatively cool and doesn't get very hot in the microwave field, whereas the pie filling and the meat and the meat juices do get very, very hot. And sometimes it can be quite a surprise where you bite into the cool pastry and then get burned by the hot filling. And the reason for this is because it's governed by their dielectric properties. And so what we can think of in the case of our metal organic framework reactions is that our linkers are acting as the pastry, so will stay cool, whereas our metal salts, solvated metal salts, will get hot in the microwave field. And so from this information, our knowledge of the underpinning mechanisms, our knowledge of the dielectric properties measurements, we hypothesized that you would have a selective heating mechanism where you're heating the metal ions in solution over the linkers for the synthesis of metal organic frameworks. So what we wanted to do was we wanted to test this hypothesis. And so we built a purpose-built reactor to be able to house a solver thermal vessel inside a microwave cavity. We wanted to be able to tune and ensure that we always have the microwave field maxima being treated on top or superimposed with the reagents to make our metal organic frameworks. I should say, for safety reasons, again, a disclaimer is that we had a blast safe shield over this because these reactions can become quite pressurized. So we housed a solver thermal vessel in there, and we had a look at how we would deliver the microwave energy and then the impact of that. So we were particularly interested in looking at different ways of delivering the energy, which requires us to be able to measure the energy absorbed by the reaction mixture. So we looked at low microwave power for a long period of time, and then changing that to a high microwave power for a very short period of time, delivering the same amount of energy, just in different ways. And then having a look at that on the percentage conversion. So in our case, the yield of the MOFs that we were producing and the quality of the MOF material, which in our particular case, we said we wanted to produce a highly crystalline material and a highly porous material. So I'm now going to show you the results of this investigation. So for our particular investigation, we wanted to focus on Mil53 aluminium. This is a very archetypal MOF. There is a lot of literature available, and also the mechanism for the formation of this MOF is well known, hence our choice. And this is synthesized from the terephthalic acid linker. You can react it with a range of metal 3 salts. In our case, we used aluminium, and we synthesized this in water, again, in keeping with the sustainability drivers that we've got in mind. And this forms the Mil53 structure. In this case, you've got the aluminium oxygen secondary building unit. Again, the linker bridges between those secondary building units, and then you've got the void space shown by these spheres. This MOF, when synthesized, can produce different phases. So there is the terephthalic acid phase, where the terephthalic acid is intercalated into the pores during synthesis. You can get the hydrated phase because we are working with water as our solvent. So you can get water present within the structure. And then you can get the open phase as well, which is the material where there is nothing within the pores. So we went ahead and we synthesized Mil53 aluminium by changing the way in which we were delivering this energy. So we fixed the energy, changed the power and the times to be able to deliver that same energy, and had a look at the yield and then the properties. So on this graph, what I've got is the average yield plotted against the average absorbed power. Note that this is the absorbed power rather than the applied power. So we were measuring the power that was being absorbed by the reaction mixture. And we can see that we get a rough trend where as the power increases, our percentage yield of this material increases, which is indicative of this selective heating mechanism. Now, you probably will notice that the yield is quite low particularly for a MOF synthesis, particularly for this particular MOF at around 34%. And the reason for this is due to the stoichiometric ratio that we were using with our within our reactor. And this is related to the penetration depth of the microwaves within this reaction mixture. So we wanted to ensure that we were working at concentrations where you wouldn't get large differences between the heating at the outside of the vessel compared to the center of the vessel. So we were aiming for a more homogeneous delivery of that energy with specific components heating within it. We can overcome issues with penetration depth by moving into continuous flow methods, which I'll talk on in the latter part of my talk. We were also able to show that we didn't produce any aluminium oxyhydroxide, which is a byproduct which can sometimes form. This is a very unreactive, dense material, non-porous, and is quite difficult to separate from the products of reaction. And so we were very grateful that that didn't occur. And to give you an idea of the timescales and the powers involved in this, we were able to produce roughly around 60 milligrams of the MIL53 with the terephthalic acid incorporated in the pores at roughly around 4.3 seconds at an average absorbed power of roughly around 4 kilowatts. So these are very, very fast reactions. Now, interestingly, we saw that we were able to have control over the properties based on the treatment parameters that we were using for this energy delivery. So when we were increasing the average absorbed power, we saw differences in the morphology of the particles and the particle size range. So what I've got here on this graph is we've taken the area of a face of the crystal and we've plotted this against average absorbed power, where the basalite A100 material is the commercially available material which is not synthesized by microwave heating, but this was our benchmark. You can see that the area of the crystal on this box and whisker plot, the particle size distribution was very, very wide. When we look at the microwave prepared materials and increasing power, we go from wider particle size distributions to narrower particle size distributions. So that means that as we go higher in power, we are producing crystals which are more uniformly in size compared to each other. And this is particularly important if you are looking at applications where mass transfer kinetics are key, such as catalysis and sorption. What we also saw was that as the power increased, we went from irregular shaped morphologies for the materials we produced to increasingly regular cubes, where we were producing quite regular cubes up at 1,700 watts. And to give you an idea of the surface areas of the materials that we were producing at 700 watts, which was our, which appeared to be our optimum, we got a BET surface area of roughly around 970 meters squared per gram, which is comparable to the commercially available material. Now, I mentioned that we were limited in the stoichiometry because of the reactor and the penetration depth associated with the way in which we were performing these reactions. So to overcome this, we moved into continuous flow methodologies and using this in combination with microwave heating. So that is the final part of my talk that I'm going to go on to now. So in our particular setup, we collaborated with researchers based at Newcastle University in the UK, and they have expertise in oscillatory baffled reactors. Now, for those of you who are not familiar with oscillatory baffled reactor technology, essentially what it is a tube with regular intervals of baffles. You have an oscillating flow where your reaction mixture goes across the baffles, and as it goes backwards and forwards over those baffles, you get vortices happening, and so this is giving you efficient mixing of your materials. But the net flow is in one direction. So essentially, your flow looks something like backwards and forwards, but going in a net direction. The particular advantages of oscillatory baffled reactor technology is that you get this excellent suspension of solid particles. You can get a really high level of mixing, even at low flow rates. So you're not limited by, say, Reynolds numbers in these cases. And again, this is a technology that can lead to process intensification. It is a well-known process intensification technology, and these are scalable reactors as well. Now, if you're interested in learning a little bit more about continuous flow methodologies, both within microwave synthesis and in other ways of heating, I do recommend that you have a look at the review article that I had the pleasure of writing with Karen Robertson and Anna Slater. So I put you in the direction of that article, and there are other excellent articles as well for those of you who are interested in continuous flow. So what we did was we designed our microwave cavity to be able to house the oscillatory baffled reactor. In our reactor setup, what we have is pumps controlling the oscillation and the flow, and we have pumps which are feeding our metal salt and our linker in through the oscillatory baffled reactor. And then we've got a microwave heated zone there. And again, we have the peripheral equipment and the hardware to be able to look at the absorbed energy and to be able to look at the absorbed power. The MOF that we chose to have a look at in this particular case was HCO1, which can be synthesized from copper salt. So in our case, we were looking at copper nitrate. You then react this with the trimesic acid linker. In our case, again, in keeping with the sustainability drivers, we had a look at synthesizing this in ethanol. And this produces the HCO1 structure, which is shown here, where you have copper paddle wheels with your trimesic acid linkers in these positions, and you've got two areas of pores, or two different pore sizes within this material. So what we were interested in looking at firstly was, are we able to produce the material at a range of different flow rates, and what capabilities do we have with the particular reactor setup to be able to produce the HCO1? I should say that these reactions were performed roughly at the boiling point of the ethanol, and so we did not use a back pressure regulator. If you wanted to pressurize, you would, or go above the boiling point of your solvent, you would need to incorporate one of those. So what we've got on this slide is the production rate in grams per hour versus the flow rate. And we wanted to just get a first look and see if we were able to produce the material at a range of different flow rates. And we can see that as you increase the flow rate, the production rate increases, which is what you would expect, because you're putting through more of the reagent, you're heating the reagents, and then being able to produce more of that because your throughput is higher. So that was an excellent checkpoint. We then wanted to have a look and see what our space-time yield was against other reactors. And given that our reaction takes place in a tube, the reactor is a very, very intensified process. And so we were able to show that we could get the highest space-time yields for any MOF produced to date using this particular setup. For those of you who are familiar with HCO and reactions between copper and trimesic acid and different solvents, you may be aware that other phases can potentially be produced, and we were able to show that that wasn't the case through our powder diffraction. And we were also able to visually observe the efficient mixing and the uniform suspension of the solids. And I'll show you an example in a couple of slides' time as to the importance of that mixing. But to give you an idea of how fast these reactions were, at the highest flow rate, so up at 100 mils per minute, our energy delivery was at 2.2 seconds, which is the fastest reported synthesis of MOFs that I'm aware of to date. So extremely fast reaction time. So it was great to see that we were able to produce the material at these astonishingly fast timescales. Now, as a key point, I've mentioned that we want to maintain the porosity of the materials that we were producing. We wanted to have a look at the effect of this as a function of how fast we were producing it, and then therefore the flow rate. And there is a marker that we use called surface area production rate, which is the amount of material based on the footprint of the reactor with the surface area of the material being produced and the time in which the reactor is being operational for. And what we can see is as we increase the flow rate, our surface area production rate, which is on the y-axis, we see that we increase our surface area production rate as we go up in flow rate. So what this is showing is that we have, not only are we producing a lot of material, but we are producing material which is very highly porous, and we're not getting any issues with loss of porosity, even at these exceptionally fast timescales. And to give you an idea of roughly the surface areas associated with these materials, we're in the order of around 1,300 to 2,000 meters squared per gram. Now, I mentioned a couple of minutes ago that mixing is really important. And so I want to demonstrate that with this particular example. So when we were mixing our materials using the oscillatory baffled reactor, we were typically getting octahedral morphologies from materials and then irregular shaped morphologies where we had many particles within our products where these particles had agglomerated together. Now, if we turned off the oscillation and just had a net flow, so we'd reduce the amount of mixing that you would get, what we saw was that we produced materials which were fused together. So you can see that these are not discrete particles which have agglomerated, such as shown on the left-hand side. We've got materials where the particles have fused together. And so if your application is such that you want to be producing a free-flowing powder or discrete particles, then you will definitely be wanting to have mixing within your reactor. So that leaves me to conclude on my talk today. So I've shown you some excellent examples of microwave heating in MOFs. So I've shown you examples in the literature in both and also from the group in Nottingham on the synthesis of MOFs using off-the-shelf systems, the purification and activation of these as well. And I do encourage you to have a look at the reviews associated with these because there's a lot of fantastic work going on out there. I've shown you from work that we've carried out at Nottingham that solvated metal 3 salts are strong microwave absorbers and that organic linkers are essentially microwave transparent. And so this is information garnered from the dielectric properties measurements. And this fits in with the mechanisms that we'd expect to see for heating with microwave fields. I've then shown you that we, using a bespoke purpose-built reactor where we delivered a constant energy, but delivered that at a low power for a long period of time or a very high power for a short period of time, we can see that the amount of absorbed energy increases the percentage yield of the MOF that we are producing. And this indicates a selective heating mechanism where the metal ions in solution heat before the heat is then transferred to the linkers during the synthesis. And this is in keeping with the dielectric properties measurements. I've then showed you that we can control the MOF particle size range and morphology by altering the microwave treatment parameters. So this can be potentially also used in combination with chemical parameters as well, such as modulators, to give you extremely high control over the particle sizes and the morphologies that you're producing. And I've also shown you that we move towards continuous flow microwave synthesis to overcome issues with penetration depth, and that incorporating oscillatory baffled reactor technology allows us to produce MOFs at a reasonably high production rate at an astonishingly high space-time yield, and that our surface areas of the materials we were producing were still very, very high. So that leaves me to thank, importantly, the people at Nottingham and the collaborators and the funders. And in particular, I want to draw your attention to Yayan Thomas Hillman and John Luke Woodliff, whose work has contributed, in particular Yayan, who really did start things off in the group, looking towards developing these reactors and conducting this work. So thank you very much for your attention, and I'm happy to take some questions.
Thank you, Professor Andrea Laybourn, for your great presentation. In the meantime, we are waiting for questions from YouTube. I'd like to ask you some. For people like me that are quite new into microwave synthesis, which reference would you recommend?
So there's quite a few references that I would recommend. So let me have a look and see if I can point it in particular. So Yayan wrote a paper on the microwave interactions of MOFs and had a look at a few examples. So I believe that references in the Journal of Materials Chemistry A. I would also point you in the direction of the recent paper that Romy Ettlinger led, which is in Advanced Functional Materials, which allows you to have a look at the sustainability aspects of that. So with the combination of those two papers, you'd get an idea of mechanisms and understanding of the underpinning science, and then the really great advantages that microwaves show in improving things such as sustainability of the synthesis. So those two I would recommend.
Thank you. I understand that this technique of MOF synthesis is quite new and innovative, and I was wondering if there are even books that you might recommend besides these references.
Yes, so going out a little bit out of the microwave heating for MOFs area, there's been some fantastic stuff being written by Oliver Capet, and his focus, I believe, is in, if I'm not wrong, is in organic synthesis using microwave technology. And so there's some fantastic books that he's written that I would recommend. If you are more into the industrial microwave heating side, there's a couple of books by Metaxas that I would recommend having a look at as well. And this is more towards developing, looking at reactor configurations and energy delivery.
Okay, I see here we have a question from Adam Ward, who's asking, with the view to bringing down the cost of MOF synthesis, how much of an impact do you think microwave heating or continuous flow technology will help compared to other methods?
Yes, that's a really good point, Adam. So microwave synthesis can make some strides towards energy efficiency and the time for reactions. And you can also have advantages in terms of the speed of the reactions and minimizing downtime, particularly if you're going into continuous flow. But a lot of so that's in terms of the energy efficiencies and the rates of reaction. But a lot of the impact from the cost of MOF manufacture is related to the metal ions or metal salts that you're using to synthesize these materials and the linkers. And so obviously that is independent of the reaction route that you take, but you would be wanting to select a reaction route that minimizes the waste that you produce from this, so that you are ensuring that all of your reagents form the desired MOF product. So that limits the costs there. But I think one of the largest hindrances is this linker, looking at the linkers and the cost of the linkers and the metal salts, particularly things like cobalt and zirconium, which are a lot more expensive, and looking at very, very intricate linkers. You can focus research in the areas of more abundant metal salts, such as iron, aluminium, and you can use more commercially available linkers, such as terephthalic acid, trimesic acid, which are cheaper than other alternatives. So it really does depend on your MOF in that particular case. But I should say that there are also other methodologies that you can use as well. So room temperature synthesis is a good one if you're wanting to look at reducing the cost, but this can increase your reaction time. And mechanochemical methods are also another very good way of synthesizing MOFs.
Thank you for your answer. Here we have another question from Arvin. First of all, he thanks you for this interesting talk you're having, and he's asking, where do you foresee microwave application? More for small scale, high value MOFs, or for large ton scale? Basically, he's asking, what is the scalability of these approaches?
Yes. So I do see microwave heating moving towards industrial scale. And the reason for this is because of the energy efficiency and the rapidity of the reactions and the quality of the materials that we are able to produce. I think the area is going very much into, quite conveniently, into the papers that are highlighted at the moment on this slide, in looking at combinations of machine learning, online optimization, and continuous flow methodologies. I think that is an extremely powerful way to be able to use microwave synthesis for high throughput investigations, optimizations, and then scale. Microwave systems are scalable, so it's going in that direction, in my particular opinion.
Another question from our audience, from Sagar Saren, is thanking you, of course, for the talk, and he's wondering if you can apply microwave heating not only for MOFs, but even for the synthesis of zeolites or activated carbon materials.
Yes, that's a great question. So Jung has done a lot of work looking at microwave synthesis of zeolites, and so I would recommend you have a look at some of their papers. There are other people also working in the area of zeolite production using microwave heating. Activated carbons, I must admit, I'm a little bit less familiar with the microwave synthesis of those. I am aware of research that's been taking place where people have been looking at activating carbon materials. So if you've got a solvated carbon and then activating using microwave heating, so there's some fantastic examples of that. And I should say that we're not limited to zeolites, activated carbons, and MOFs. Microwaves have also been investigated for covalent organic frameworks as well, and for other types of porous organic materials as well.
Okay, I have a question always regarding the microwave application, specifically about the oscillatory baffle reactor. Where else do you think it can be used besides the synthesis of sorbents?
Yes, fantastic. So Other areas that I've seen oscillatory baffled reactors being used are in the petrochemical processing. I would direct you into the group of Adam Harvey, who's based at Newcastle. They've done a lot of work on developing oscillatory baffled reactors. So they've been looking at petrochemical processing, biofuel processing, things like that. So there's a lot of other applications. Essentially, you can use oscillatory baffled reactors, or it's a technology that you would want to consider if you need to have control over the mixing, and it can also be used if you've got long timescales for your reactions where you are wanting to operate at low flow rates. So for slow reactions, because you are not limited by the flow rate because you've got the mixing with the baffles in those scenarios. So you can do very, very low flow rates where your Reynolds number might be low. And so you're still able to achieve efficient mixing in those cases. So I would recommend having a look at Adam Harvey's work. I'm just going to see if I can skip out and go to the last slide. Sorry. The reference that so I touch on it a little bit in the quid pro flow, getting tongue-tied. Quid pro flow article, I touch on oscillatory baffled reactor technology in there, but as I mentioned, I definitely recommend having a look at Adam Harvey's research group. I do believe Adam's also written some books on oscillatory baffled reactor technologies as well. So I'd encourage you to have a look there if it's of interest.
Thank you so much. If you still have time, I'd like to ask a last question.
Sure, yeah, happy to take the last question.
In slide 10, you presented that MOFs made in microwaves have greater uptake. I think it is because of the production method that causes less defects. Is it that reason?
So there are two aspects to microwave heating. If you are, and it depends on the reaction rates of the materials that you're producing. So if the reaction is very, very fast, you can get less defective materials. But if your reaction rate is slow and you microwave for a very short period of time, you're able to isolate intermediates from your reaction, and those intermediates may contain defects. So it depends on the materials that you're trying to synthesize and the reaction rates of those. An advantage with microwaves is you can microwave for a longer period of time and get less defective materials or pristine materials. Or if you go for very, very short reaction times, you may be able to look at alternative phases of materials that you've produced, and also be able to isolate defective materials. So it depends on a balance of those, the treatment conditions and the rate of reaction for forming your product of interest.
Thank you, Professor. I think with that, I can give back the control to Nick, and thank you so much for your presentation.
Thank you very much. And thanks again for inviting me to talk.
Thank you, Professor Laybourn, for your presentation, Synthesis of Metal Organic Frameworks Using Microwave and Flow Technologies. We also thank all of our attendees for joining this webinar and hope that it was both educational and enjoyable. An edited version of this webinar will be posted on the IAS YouTube channel and Bilibili with an announcement on the IAS Twitter feed. The hope is that the work discussed here today will be a useful resource for the adsorption science community in the future. We are currently organizing webinars for both October and November, but currently do not have any confirmed dates for these. Announcements regarding the next webinar and other IAS online events will be posted on our Twitter feed and through the IAS mailing list, With that, we thank you for joining us and hope that you'll join us again soon.